Let's have a look at how we can build circuits from logic gates to do arithmetic on binary numbers. So in a previous video we looked at binary and how we could do binary arithmetic. If we want to add these two numbers together, we do it the same as we would do it in decimal by starting in the least significant column and adding the numbers together. So if we have 1 and 0, the output is 1. If we have 0 and 0, the output is 0. If we have 1 and 1, the output is 0 carry 1. And if we have 1, 1 and 1 carry in, the output is 1 carry 1. So let's have a look at how we can build some circuits to do this. So we're going to take a look at a half adder circuit first. This is dealing with one column in our sum, so it's just dealing with the input values and the carry out value, but it's not dealing with the carry in value. The full adder takes into account the carry in value, so that's a bit more of a complicated circuit where we've got the carry in value and the two inputs and the carry out value. And then we'll have a look at we can string these adder circuits together to build an ALU which can add two bytes together. And then we'll have a look at how we can change that circuit to make it subtract. So for the half adder, we've got two inputs and we've got the output and the carry out. If both inputs are 0, we want the output and the carry out to be 0. If input 1 is 0 and input 2 is 1, we want the output in this column to be 1 and the carry out to be 0. If input 1 is 1 and input 2 is 0, we want the output to be 1 and the carry out to be 0. And if both inputs are 1, we want the carry out to be 1 and the output to be 0. So how can we build a circuit to do this? Well, if we look at the columns, and if we remember back to the logic gates video, this is exactly an exclusive OR, because we want 0 if both are 0 or if both are 1, but if one or the other but not both is 1, then we want the output to be 1. So this is a truth table for an exclusive OR. If we look at the inputs and the output, this is exactly what we need for the output column. And if we look at the carry out column, again, we can represent this with one logic gate, and this is an AND gate. So if both inputs are 0, or if only one of the inputs is 1, then the output is 0. But if both inputs, one and the other, is 1, then the output is 1. So that's what we need to do a half adder circuit, an exclusive OR gate and an AND gate. So let's have a look at that in action. So this is a model of the half adder circuit. So we have our two inputs with the switches, input 1 and input 2, and this LED here represents the value for the column that we're doing the sum in, and this LED here represents the carry out. So for the value we've got the XOR gate, and for the carry out we've got the AND gate. So if we input two zeros, we get 0 carry out 0. If we enter 1 into one of the inputs, we get 1 carry out 0. If we enter another one, we get 1 carry out 0. But if we do both, the output goes to 0 and the carry out goes to 1. So that's exactly what we want for the half adder circuit. So the half adder's dealt with this much of what we want to do. For the full adder, we're going to take into account the carry in bit as well. So this box here represents what we've got from the half adder. The values beneath it we still need to work out. So if we look at these first, the output values, if we look at what the output was with the half adder, 0, 1, 1, 0, if the carry bit is set, we want it to be 1, 0, 0, 1. So we can add another exclusive OR gate to the output value, and if the carry in bit is set, we'll use the exclusive OR gate to reverse the output. So So our original half adder was this exclusive OR and this AND. If we put another exclusive OR and connect it to the carry in bit, that will reverse the value of the original exclusive OR, and that will be our output value. Now if we have a look at the carry out bit, this is either a combination of the original exclusive OR gate, which would give us these two ones here, or if both inputs are set and the carry in bit is set, then we want it to be 1. So we can do that like this. So we have the carry in bit connected to an AND taken from the original exclusive OR gate, and we want the result of the carry out to be either that, or if both bits are set. So they go through an AND gate. If both of them are set, they'll feed into the OR. So this is our carry out bit, and this is our full adder. So let's have a look at that in action. So the easiest way to think of the full adder inputs is just 3 separate values. There's one input, the other input, and the carry in. So let's just test every combination of 1 and make sure that the output we get is an output of 1 and a carry out of 0. So if this one is on, the output is 1, carry 0. If this one is on, the output is 1, carry 0. And if the carry in bit is on, the output is 1, carry 0. Now any combination of 2 should give us 0, carry 1. So let's try these two. The output is 0, carry 1. These two, 0, carry 1. And finally these two, 0, carry 1. If both inputs are on and the carry in is on, we should get 1, carry 1. So there's all 3 of them on. The output is 1, carry 1. So that's a full adder circuit. So I've taken 8 of these full adder circuits and joined them all together. I've taken the carry outs of each adder and fed it into the carry in of the next adder. And then I've got 2 input values that I can enter. The first set goes to the input 1s of each of the adders, and the second set goes to the input 2s of each of the adders. And then I've got an example byte arithmetic sum that we can do to test it. So if we put the values in 0, 1, 1, 1, 1, 1, 0, 1, and the other value 0, 1, 0, 1, 1, 1, 0, 0, we can see that the output is 1, 1, 0, 1, 1, 0, 0, 1, which is what we want. So that's a basic set of full adder circuits which is performing a sum on a byte value. So in the video on binary, we looked at how we could represent a negative number in binary using 2's complement. To do this, we take the positive value, reverse all the bits, and add 1 onto it. On the right, I've extended the ALU circuit now and given it a switch where we can switch it into subtract mode. For the second input, we've taken all of these values through exclusive OR gates which are connected to the switch. The exclusive OR gate, when we put input into one of the inputs, it will reverse the other input for the output. So this switch is going to reverse all of the bits of the second input before it goes into the adders. We've also taken a line off the switch into the carry in of the least significant bits adder. So that will add 1 onto it. So if we put a value into the second input, say we put the value 3, we have 3 in the output from the adders. If we flick the subtract bit, it will turn this into a -3, and there's -3, 1, 0, 1 in binary. So now if we put the value, say 5, into the first input, which would be 4 plus 1. We have the value 2. So we've subtracted 3 from 5, we've got 2. If we switch the subtract switch off, we'll then add 5 and 3, which is 1, 2, 4, 8, as we'd expect. So this modification here allows our ALU to both add and subtract depending on whether this switch is set. So in the next video we'll take this ALU circuit and add it to our CPU model. We're building a full model of a CPU, and if you'd like to follow the videos as I make them, then click subscribe. Thanks for watching.